Okay, we're going to looking at two different approaches to design the concrete shear using both NZS 3101 and modified compression field theory to check the shear capacity of a thick slab. So what we got here is a thick slab that is built about 1960s, and the slab was designed to just top and bottom reinforcement without any shear reinforcement at all. So, and it is quite deep slab. So, first of all, we're going to use NZS 3101 to check what's the shear capacity of that slab. So, what we're looking at here is a cantilevered section of the slab. So, at here, we've got a maximum shear demand as 595 kilonewtons. But also we have a hogging moment right here. So, we're going to use that hogging moment in our modified compression field theory to design the shear. But here, let's just looking at the shear only. So following by 3101 approach, the equation we are using is that there are two components to design a shear. One is the contribution of the concrete, another is contribution of the steel. Since we have no steel in here, then we'll be just using the contribution of the concrete, which is a small VC here. And then small vc, and we're going to use in the Ka factor, Kd factor, and a Vb factor here. And we also have a Kn factor that is accounting for any axial loads. For example, if you have pre-stressing loads here and or axial loads in here, but in this case we have 0. So, and if we have 0 for the Kn factor, your Kn instantly becomes 1 over here. So in this case here, I just dismissed the Kn for the VC calculation. So first of all, we're looking at the Ka factor. Assuming back then they were using normal aggregates like around 10 or 19 mils, but here I'm just taking 0.85, just assuming they're going to use a very small aggregates, just to be conservative. But you can use 1 to work out your calculations. Then we're going to use the Kd factor, and the Kd factor we can just follow by the equation in 9.3.4. That is accounting for the depth of that. However, if you have at least the nominal shear reinforcement in your concrete, your Kd factor is instantly becomes 1 as well. So, but in this case here, we don't have any shear reinforcement, so we go a little bit deeper to using the empirical method to find out what's the Kd factor that accounts for the depth and without any shear reinforcement, and it gives me 0.76. And then we're going to work out a Vb factor, and it's a range between 0.08 and 0.2, and we just get 0.143. And that within that range, that is okay. So we adopt that to calculate our shear stress contributing to concrete is 0.485 MPa. And then we use that shear stress times our effective cross-section area, that's just the B times D, and we're talking about a meter strip width, and the depth of to be 1193. I have deducted the 50 mil cover just to be accurate, and then eventually I get the concrete shear capacity is 578 kilonewtons. That is almost close to 595. So this is pretty interesting, because back then they're probably thinking about Ka. If you were thinking using Ka as 1, and you would probably ended up the same amount of the capacity and to demand. So back then they were saying that okay, the concrete relying on the concrete shear strength is probably okay. So the other thing is because the concrete shear capacity has to be tested, right? So back then in laboratory environment, if you were going to test in a small scale concrete, but it's not necessarily reflecting the actual behavior of a actual concrete. If you test about like a small beam, it's a 200, 300, that was a little small beam, but the deep beam never been tested. if never been tested if you adopting the empirical formulas that derived from the small section and use that formula to design your deeper section, and that's where things doesn't line up. So that's probably can explain a bit why the old structures tend to fail in shear in this case. Okay, next we're gonna looking at modified compression field theory. So this was recently in the recent decades was developed in the University of Toronto and has been adopted in ACI code and and the Canadian code as well. And New Zealand is probably thinking about doing a provision of the shear design, but we will see. So the modified compression field theory is it's a good tool. It accounts for the looking at the stresses at the concrete and looking at the size, cracking size spacing, and that is to do with the aggregate size here, and eventually we're gonna so this is a beta value that is substituting all the Ka, Kd, and Kn and the Vb factors in here. That all of them becomes one beta value. So the beta value accounts for the strain in the concrete and the size effect, the cracking size in the concrete, and eventually you get your beta value in here. So you can see this strain calculation accounts for your moment, the ultimate hogging moment, and your maximum shear at here, the location. And then you get your, once that, you're going to determine your effective cracking size as ZE. And as ZE is a function of the size of SZ and aggregate size AG. And so I believe there's a note in here saying that the SZ is either JD for members without shear reinforcement or 300 for members with shear reinforcement. But in this case here, we don't have any shear reinforcement, so I'm adopting my SZ to be 1193, deducting the 50 mil cover. So follow the equations here, and we get our VC to be 0.343, and we're going to use that times our section length and width. We're talking about a 1 meter strip and the 1193 to be the section depth. So we get our concrete shear capacity is only 409 kilonewtons. That is vastly smaller than the demand. So yeah, so compression theory can be a really good tool if you were designing a really deep beam, such as a foundation beam like a meter deep, or a transfer structure that's about 800 meter deep, or bridge slabs. And I think it's worth to looking at the modified compression field theory to work out your shear capacity and use that to determine your shear reinforcement accurately. Okay, thanks for watching.